In this video, I'll talk more about using system concepts in electric circuit analysis. If I identify the system inputs and outputs as the voltage and current at a pair of terminals in a circuit, the voltage-current characteristics at those terminals becomes an input-output equation. Now let's talk about some specifics relative to modeling circuits as systems. Recall that when we model a physical device as a system, we're looking for a mathematical relationship between the input and the output. The equation expressing the output as a function of the input is called the input-output equation. In electrical circuits, voltages and currents are signals, so they're appropriate choices as system inputs and outputs. That means that if we think of an electrical device as being a system, the relationship between voltages and currents applied to the terminals of the device can be written as an input-output equation. We're already used to modeling circuit components with the relationship between the voltage and current at the components' terminals. That means we can think of the voltage-current relationships as being an input-output equation. The rest of this video will expand on this concept. Most of the circuit components in this course will have two terminals. The component's behavior can then be described by the mathematical relationship between voltage and current across these terminals. This concept can be generalized to describe an entire circuit in terms of the voltage-current relationship across any two terminals of the circuit. Since we're representing an entire circuit network as a mathematical relationship across two terminals, these are called two-terminal networks. This approach has a couple of distinct advantages. First, it can help us isolate different portions of an overall system. If we know of two terminals where two subcircuits will be interconnected, we can specify the desired voltage-current relationship at those terminals. This relationship can then be used to analyze or design the subcircuits individually. Breaking up tasks in this way is essential to design of a large-scale system in which different teams may be responsible for different portions of the system design. This approach is consistent with the system-level approach I've already presented, and it has all the benefits of that systems approach when doing design and analysis. Since voltages and currents can be represented as signals, circuit design and analysis can easily be placed in a systems framework. Just think of the voltages and currents at a pair of terminals as inputs and outputs to a system. Either the voltage or the current can be chosen as either the input or the output. The definition of inputs and outputs is generally somewhat arbitrary. If the voltages and currents at the terminals of a circuit form the inputs and outputs of a system, then the voltage-current relationship at a circuit's terminals is a valid input-output equation for the circuit. In the rest of this video, I'll do examples of this process and place these concepts in the context of how we already analyze circuits. My first example of a system in electrical engineering will be a resistor. If we define the voltage drop across the resistor and the current through the resistor as shown, the voltage-current relationship is just Ohm's law. V is equal to I times R. This relationship can be represented as a system in a couple of different ways. If I define the current as the input and the voltage as the output, the system just multiplies I by R to get V. If we want to use our system's approach to determine the voltage resulting from a 1 amp current source connected to a 5 ohm resistor, we can use this formulation. 1 amp is the input, I multiply that by 5, and the output voltage is 5 volts. On the other hand, we could assign the voltage V as the input. Now the system multiplies V by 1 over R to get the current I. Connecting a 5 volt source to a 10 ohm resistor and finding the current is probably better modeled by this system. 5 volts is our input. That's divided by the resistance to determine the current, which is 1/2 of an amp. Either of the system models I showed here are fine. They just have different roles assigned to the input and the output. Now let's extend this idea to a network of resistors. Suppose we have this combination of resistors and we define a voltage difference and a current as shown at these two terminals. We've already determined that the voltage-current relationship at these terminals can be expressed as an equivalent resistance, which is just the ratio of the voltage V to the current I. For this circuit, we know that we can combine these two resistors in parallel to get an equivalent 2 ohm resistance. Then add that 2 ohm resistance to this 2 ohm resistance to find an equivalent 4 ohm resistance. But let's take a look at this problem from another standpoint. We know that we want to determine an equivalent resistance, which will be the ratio of voltage to a current applied across these terminals. So let's hypothetically connect a 1 volt source across the terminals and calculate the current resulting from that source. Once we find the current, we just divide the voltage, 1 volt, by that calculated current. If I define this as a node voltage, VA, and then do KCL at that terminal, I get VA minus 1 volt over 2 ohms, the current in this direction here, plus this current, which is VA minus 0 over 3 ohms, plus this current, which is VA minus 0 over 6 ohms. If I solve that for VA, I get VA is equal to 1/2 of a volt. The current I is equal to this voltage, 1 volt, minus this voltage, VA, over this resistance, 2 ohms. That's just Ohm's law. So 1 minus 1/2 over 2 is 1/4 of an amp. Now my resistance, REQ, is just this voltage, 1 volt, over the corresponding current, 1/4 of an amp, which is 4 ohms. This result agrees with the circuit reduction approach, although it is considerably more labor intensive. This problem could also be approached by applying an arbitrary current, say 1 amp, calculating the resulting voltage. The equivalent resistance would then be that voltage divided by the applied 1 amp current. However, let's do this problem slightly differently. I'll connect a current source with an unspecific current that will be my independent variable I. Now I'll calculate the voltage difference V in terms of I and then take the ratio of V to I to get the equivalent resistance. If I call this a node voltage, VA, Ohm's law tells me that VA is equal to this voltage V minus the voltage difference across this resistor, which is 2 ohms times I. Now using this to write KCL at this terminal, the current going in here is I. I'll make that a negative contribution, plus this current, which is VA over 3, which is V minus 2I over 3 ohms, plus the current through the 6 ohm resistor, which is also VA, or V minus 2I over 6 ohms. That sums to 0. Multiplying through by 6, I get minus 6I plus 2V minus 4I plus V minus 2I is equal to 0. Now if I group my terms, I find that 3V is equal to 12I, and V over I, which is the equivalent resistance, is now just 12 over 3 or 4 ohms. Once again, this result gives the same result we'd expect from circuit reduction techniques. Now let's look at a problem that contains a voltage source. Circuit reduction techniques won't help us here, since we can't combine a resistor and a voltage source. The systems approach, however, is really general. In this case, let's hypothetically apply a voltage source with voltage V to the circuit and find the corresponding current I. Ohm's law here says that I is equal to V minus Vs, the voltage difference, over the resistance R. If I solve for V from this expression, V is equal to R times I plus V sub S. If I plot this equation, I get this curve. The y-intercept is the voltage of the voltage source, Vs, and the slope of the curve is the resistance R. The slope of the IV curve seen across these terminals is still the equivalent resistance seen at the terminals. Now let's look at another way of finding the equivalent resistance across these terminals. To do this, I'll kill the source in the circuit. Killing a voltage source replaces the source with a short circuit. If I make that change to the circuit, the equivalent resistance across these terminals is just this resistance, R, the resistance with the source killed. This gives us a simpler approach towards determining the slope of the IV curve across these terminals. With this in mind, let's take a closer look at the concept behind killing a voltage source. Resistance is the slope of the voltage versus current curve. This is the voltage current curve for an ideal voltage source. If we retain the same slope of the curve but remove the offset, the voltage due to the voltage source, we get this line. This line is the same as that for a short circuit. So replacing the voltage source with a short circuit retains the same slope or resistance and just removes the offset. Now let's find the voltage-current relationship for a circuit containing a current source. Circuit reduction techniques let us down again since we can't combine these two elements. So let's apply a voltage to the terminals and calculate the current resulting from this voltage source. If I do KCL here, this current is V over R, so I plus IS, those are both entering the terminal, is equal to the current leaving, which is V over R. If I solve for V, V is equal to R times I plus R times I sub S. If I plot this equation, I get this curve. The y-intercept is the resistance times the source current, and the slope of the curve is the resistance R. The slope of the IV curve seen across the terminals is still the equivalent resistance seen at the terminals. As with the voltage source, let's calculate an equivalent resistance by killing the current source. Killing a current source replaces the source with an open circuit. If we make that change to this circuit, the equivalent resistance at these terminals is just the resistance R, the resistance with the source killed. Again, we get a simpler approach for finding the equivalent resistance seen across these terminals. Now let's take a closer look at the concept behind killing a current source. Resistance is the slope of the voltage versus current curve. This is the voltage current curve for an ideal current source. If we retain the same slope but remove the offset, the current due to the current source, we get this line. The resulting line is the same as that for an open circuit. So replacing the current source with an open circuit retains the same slope or resistance and just removes the offset. Thinking of the voltage-current characteristics at a pair of terminals in a circuit as an input-output equation allows us to develop an extremely powerful analysis tool, Thevenin's theorem.